Scientists have recently discovered the largest ever neutron star. This star is so large that it is right on the edge of turning into a black hole. Let's find out more about these types of stars and compare the mainstream and the EU models. In the mainstream model of a neutron star, it is believed to form when stars of about 8 times the mass of our own Sun explode in a violent supernova. This often ejects the outer layers, creating a huge nebula, and this leaves a small dense core that continues to collapse. At this stage, the star is thought to have used up all of its fusion fuel, and therefore there is no outward pressure to halt the inward collapse. Gravity causes the remaining matter to compress so much that the protons and the electrons combine to make neutrons. As they are compacted and squeezed down, it ends up with a radius of only 20 kilometers. And they are thought to be so dense that a single teaspoon would weigh as much as 1 billion tons. The process of formation is thought to give the stars their rapid rotation. Some can spin as fast as 40,000 times a minute, and this spin rate cannot be maintained, and the star's rotation should slowly decrease over time. Some of the neutron stars even have jets of material streaming out from them at nearly the speed of light. And here is where the story starts to become murky, as there really is no clear mechanism as to why these beams should be there in the first place. They are generally referred to as pulsars, and it is thought that material from a companion star falls onto the surface of the star, and this material then gets ejected along the poles. The problem is that this requires a strong magnetic field to be present, and there are currently no good theories as to how a neutron star is able to have magnetic fields. So why do we think that these stars are so dense and so small? In order to measure the mass of these stars, astronomers have to use neutron stars which are in binary systems. And they use something called the Shapiro effect, which means that when electromagnetic waves pass by a massive object, they are slowed down without any effect on their frequency. So the electromagnetic waves from their companion will sometimes pass close to the neutron star, and this will cause the delay, and by measuring the difference they are able to estimate the mass of the neutron star. Now the radius is altogether more difficult to measure, and they tend to be very imprecise and unreliable measurements. They may in future be able to improve this with X-ray spectroscopy. It is thought that a neutron star cannot be larger than about 2.2 times the mass of our Sun, and anything over 3 times would automatically form a black hole. So this newly detected object is right on this acceptable limit. Is there a different way to look at neutron stars within an electric and plasma universe? Let's start by examining the formation process. We know that these stars are left over after what we term a supernova explosion. Here, a violent brightening event is often linked to an expulsion of the outer layer of the star. There are many examples that I discussed in the stellar evolution episode that show this characteristic brightening and expulsion of a material in stars which still leave a visible star behind. There is also evidence that some stars undergo this process regularly, rapidly brightening with an expulsion of material. So let's first deal with a mechanism for this process. We know that in the EU model, stars are driven electrically. A fair assumption is that the intergalactic filaments supply part of this incoming current. The speed and flow of this filament is likely to be affected by other magnetic fields in the surrounding area. If we also consider Don Scott's model of the Birkeland current, it can easily be seen that if you were on a filament on the outside, your path would take you closer and further away from the center, where the magnetic field would be stronger. This could have an effect on the speed of the movement of the flow, and this in turn would have a dramatic effect on the star and may cause what we see as a brightening event. We also think that a possible model for binary formation is that a sudden change in the incoming current can cause a star to effectively split in two. Is it therefore possible that a smaller change could cause just the surface layer to separate? Now, looking at the Sapphire project, we also see double layers forming above the surface. Hannes Alfvén was the first to underline the power of these structures. When they become overloaded, they can explode, releasing a vast amount of energy and plasma. Is another possibility that these double layers above the surface explode, causing the sudden brightening and the expulsion of the plasma that we call a supernova. The rotation rate and the formation of beams in the standard model could be explained in a different way. If the star is electric, then no rapid rotation is required. Instead, it could be that this explosive event caused the star to start pulsing. Charge flows in, builds up, flashes, and then the process repeats itself, but this happens rapidly, almost similar to a Tesla coil, creating a rapidly pulsed signal. From the Sapphire project, we also know that the Sun can act like a transistor. It is a far more complex beast than a simple ball of gas. And what we have not really considered is how a star would behave if parts of the system were changed or damaged. Now, this would be an interesting extension to the Sapphire project once they are well beyond the next phase. But what about the Shapiro effect? Well, here too there is a different way to look at this. We know that as the two stars orbit each other, there is a delay to the propagation of the signal. The Shapiro effect can also be explained using the idea of electron density, and this causes predominantly radio and microwave signals to be refracted, but not the frequencies of visible light and above, due to the plasma resonance. The greater the plasma density, the greater this effect will become. So could the explosion of the double layer cause a massive increase in the electron density? Could it be that this damaged star leaks huge amounts of electrons from its surface compared to a normal star? What about those beams out of the poles? In Hannes Alfvén's solar model, there are currents that flow out of the poles of stars. This is, however, not reflected in Don Scott's model of a star, where the currents flow in at the poles and out along the equator. The difference here is that in Alfvén's model it is not driven externally, but in Don's model the stars are from the galactic Birkeland currents. Now, when Hannes Alfvén scales his model up to the size of a galaxy, then we do start to see these relativistic jets appearing. So is it possible that something causes a sudden increase in the available energy to cause the star to start producing these beams just like a galaxy? Could it be that a plasmoid model of a star would work better? If we examine Eric Lerner's model, then we see these jets do form out of the poles of the plasmoid. And in essence, his model is very similar to Hannes Alfvén's model, where Alfvén never made any assumptions about the interior of stars nor the interior of galaxies. Can we simply overlay Lerner's model onto Alfvén's? I'm not sure it's that simple, because I do believe that parts of the stars are indeed driven externally. So the truth lies somewhere in between these models. Don Scott's models cannot really predict an outgoing beam out of the poles, but Lerner's model can. So is it possible that actually both occur at the same time, but in a normal star model the beams out of the plasmoid are too weak, too small, and are just circulated internally? And then when something happens and the current increases or additional material is fed into that plasmoid, that it comes to life? I mean, there are many questions, because again it comes back to this notion of, is it possible to add additional material to keep that plasmoid going beyond its normal life? Or is it as in Eric Lerner's galactic model, which I know you haven't seen because that actually comes out on Monday, where the plasmoid actually dies and then is recreated over and over again? So could that process be actually what is going on inside of the sun? I don't know, these are still huge questions to be answered. Now, this is a topic that I do want to revisit to get more up-to-date understanding of the different models, and to try and tread that line which joins some of these models together, and especially in light of the Sapphire results. What can we gain from that we can help to understand which model might work better than other models? There's a lot of food for thought. As always, be brave, be curious, the truth is waiting for us. Until next time.